Hi, welcome to today's Markforged webinar. My name is Sondej, and I'm an application engineer here at Markforged. Today we're going to be talking about how 3D printing can dramatically improve the way you design and produce end-of-arm tooling for industrial robot arms. I'm going to show you a couple of examples of how Markforged customers are using printed tooling to drive their business's bottom line. And we're also going to go through a really interesting design challenge that was posed to me recently by a customer. We've got a lot to cover today, so let's get started. I always think it's really helpful to know where we're going. So before we dive in, here's a few key ideas that I want you to take away from this webinar. First, we're going to show you how you can cut weeks of lead time out of your development cycle, generally by 3D printing your end effectors. We're also going to show you how to significantly reduce the mass of your end-of-arm tooling, which will allow you to either carry more payload with your existing arm, run your arms faster, or allow you to implement a smaller, less expensive arm to accomplish the same task. We're also going to see how you can 3D print really conformal custom tooling. That's going to allow you to give more gripping contact area than what's possible with machine tooling. And finally, this one's really important to me. I want you to spend less time waiting around for tooling and see results faster from your engineering process. So hopefully we can show you how to make your development cycle a lot more fun too. Just so we're all on the same page, I want to quickly define what we're referring to when we're talking about end-of-arm tooling. So generally what I mean by this is anything past the wrist of your robot arm. So what you're seeing illuminated here. And that could include the superstructure of the end effector. It could include the gripper, the concentric gripper you see here. And it can also include the jaws, the actual final pieces of the arm that actually touch and manipulate any sort of parts that you're moving through your process. So the end-of-arm tool could be all of these things, but when we're talking about where we're actually going to 3D print components, we're really referring to mostly the jaws, which you see highlighted here. And those are the components that generally are highly custom, they're highly conformal or complex, and they generally require a lot of machine time or CNC machining time to actually produce. And so in general, that's what we're talking about when we're talking about end-of-arm tooling, and that's what we're going to focus on today. So let's talk about what we're going to show you today. And we're going to briefly talk about why you should 3D print your end-of-arm tooling. We're then going to go into a couple quick case studies and success stories from some of our customers in the manufacturing realm that are using 3D printing for their end-of-arm tools today. I'm going to take a step back and then explain a little bit about how 3D printing works, as well as how Markforged's continuous composite fiber process works as well. And then we're going to do a quick demonstration and show you how easy it is to go from a CAD model to your part printing in as little as 15 minutes if you set things up correctly. And finally, I talked about this before, but I'm going to go over a design challenge that one of my customers that I was working with posed to me, where we couldn't quite use just 3D printing to solve their problem. So that was kind of an interesting challenge as well. So let's talk about why you should 3D print your end-of-arm tooling. Well, there's a couple reasons. First, it's going to allow you to have much faster design iteration cycles, taking your lead time on getting results and tooling back from weeks of lead time to maybe a day or two. You're also going to see a massive cost savings generally. We see very often in the field greater than a 90% cost reduction versus an external vendor or even an internal machine shop. And there's additional secondary benefits of cost reductions when you can iterate quickly and catch problems before they may happen in the field. We talked about this already, but we're going to talk about improved part manipulation. So it's going to be much easier to produce a really complex geometry. So in some cases, you may not have designed a end-of-arm tool the way you really wanted it to be. You designed it to the way that was machinable. And 3D printing gives you a lot more control over geometry, so you can oftentimes design a much better part. And finally, we're going to talk about how to have more fun and problem solve nearly in real time rather than with weeks of sort of delay. My central idea here is that tooling development is wasting your time. And we're going to look at that by comparing 3D printing with Markforged versus a conventional process like CNC machining, which is usually how a lot of this end-of-arm tooling is generally produced. So with CNC machining, for example, you're still going to have to develop your CAD model or your 3D model, the same as you are with 3D printing. But once that model's developed, you have to send that off to either an internal shop or an external vendor. So oftentimes, I imagine you're going to either have to build a drawing or at least go through a internal PO process in order to get that part sent off to your machine shop. Once it's at the machine shop, there's usually a backlog. And what we see with our customers on average is that their internal or external machine shops see somewhat between a 1 to 3 week average backlog before they're able to actually get to a lot of our customers' parts. So once that backlog's actually burned through and they're able to actually get to machining your part, there's going to be CAM programming to do, stock setup, tool prep, and then finally actually the machining of your actual parts. And once that's done, it's put in the mail and put out for delivery. So that adds up to quite a long time to get a single design iteration back. And you may be seeing 2 to 4 to 5 weeks before you're even getting that first results back from your design. But with 3D printing, it's much simpler. So you're going to cut out a lot of those steps in the process, and you're going to reduce your total design iteration time significantly. There's no need to build a drawing or generally go through your internal PO process, and there's generally a much smaller backlog on a 3D printer. What we see is that because the printer can run on nights and weekends, it's much often, or it's very more likely that a customer has a much smaller backlog on their 3D printer than at their machine shop. The actual 3D printing process itself may take a little bit longer, maybe a few more hours longer than actually machining your tooling, but because it's able to work nights and weekends, it overall is a much faster process. And then finally, generally the 3D printer is going to live on site, and so there isn't a delivery time that's associated with an external vendor, apart from an external vendor. So what we see is that, as you can see here, the total print time is much shorter than your machining time, and so you're getting a design iteration cycle that's much faster. And when we compare this to the cycle time for a machined part, we can see that you actually can get multiple design iterations done in the same time with the 3D printer versus a machined component. And this means that in the same amount of time, you're going to be able to iterate much faster and get a much more mature design with a 3D printer than with machining at a shop. So let's talk about a couple of our customers' success stories and successful use cases with 3D printed end-of-arm tooling. This is generally going to be in the manufacturing realm. So our first example is DIXON Valve and Coupling Company, who's been a Markforged customer for a number of years now. And they've had a ton of success by 3D printing a lot of their end-of-arm tooling to manipulate generally castings and work-in-progress stock between various CNC machining processes. And so their robot arms are bringing these couplings and castings from one machining process to another. And at DIXON Valve, they've seen a massive impact. So they've seen lead time decrease significantly. Before, it took them 2 to 4 weeks generally to get tooling back that they can now print in 2 to 3 days. For rush tooling, jobs they really need quickly, they've brought rush tooling's lead time down from 3 to 5 days in the past to 24 hours or less. And as far as cost goes, they've actually saved quite a bit of cost, and they internally project that they're saving about $32,000 on average per project that they've used Markforged technology heavily on. So generally that they've heavily printed a lot of grippers and end effectors on the ends of their robot arms. They actually saw a break-even ROI in a month and a half, so they paid off their printers in about a month and a half on all of their printers as well. Another great success story is PROCOBOTS, who makes mobile robotic machine tending solutions for CNC equipment. So they make these modular robotic arms that make it easy to add automated part loading and unloading capabilities to your existing CNC machines. The picture you see here is an example of the types of grippers and end effectors that they produce with their Markforged printers to deliver really strong conformal tooling to their customers. And they've seen some massive big business impacts at PROCOBOTS. They're seeing decreased lead times from 7 days from their external vendors down to about 21 hours for some of their grippers. In fact, they actually bring their printers on site with them when they do customer installations and deployments in order to print any sort of custom tooling or additional tooling they need at that time. And they also have seen some massive cost savings as well. They're really seeing about a 97% decrease in cost of their 3D printed end effectors versus their machined ones. So really big business impacts to them as a company. Another example I have is from one of our customers in the packaging industry. And this is actually a vacuum end effector for picking up flat pack cardboard boxes. And the interesting thing here is that the suction cups at the end of these, the green suction cups here at the end of the end effectors, will hold on to those cardboard boxes as they're picked up. And the cool thing about this end effector is that there's actually internal vacuum channels in this end effector. So the blue tubes you see is a main vacuum line coming into the tool. But internally, there's a bunch of channels that'll actually distribute that vacuum to each of the individual 8 suction cups at the end of that gripper. And it's really cool because that's all 3D printed and designed in, and there's no additional hardware to distribute that vacuum throughout the end effector. And so the big impacts that this has had for them have been a huge reduced tangle hazard. So they got rid of about 8 different tubes in this end effector. And so that really presents a opportunity for them to reduce the potential for that end effector to tangle or have its vacuum tubes tangle while it's moving around picking up boxes. There's also a huge impact because that end effector is much lighter than a machined one. And so in a high-speed robot like this, lighter means there's less momentum and they can move that end effector much faster while moving through their picking and placing those cardboard boxes. And finally, they're also able to have much, as we talked about before, they're able to rapidly iterate through new designs. So when they want it to go from 4 suction cups to 8 or test out a bunch of different designs to position the suction cups in different locations, it's really quick and very easy for them to iterate through a bunch of different designs and choose the best one. So hopefully those 3 customer examples showed you why you might want to 3D print your end-of-arm tooling. But let's now take a step back and actually talk about the 3D printing process in general and how a part is made. So all 3D printing processes are generally going to consist of 3 main steps. First, you're going to need to use your CAD package of choice and create a 3D model of the part you want to make. Then you're going to bring that model into a slicing software, which is going to prepare the model for printing and generate some machine instructions for the 3D printer. And then finally, you're going to send those instructions to the 3D printer and kick off a print. Now, those steps are the same across most 3D printing processes, and this is actually a great graphic from our friends at 3D Hubs. There's a wide landscape of different 3D printing technologies out there, and I think in this graphic here, there's about 15 different types it's showing, 15 different types of processes. We're going to talk today, though, specifically about material extrusion and extrusion-based 3D printing, which is one half of the 2 processes that Markforged uses to produce the strongest parts in this category. So extrusion-based 3D printing at its core is kind of like a precision hot glue gun. It's called fused filament fabrication, or FFF sometimes. But you're basically taking a plastic filament feedstock and you're melting it through a nozzle and you're laying it and using that to produce a part layer by layer, 1 layer at a time. So what that looks like, and I'm going to use this example of a end effector a couple times today. You're going to have this end effector, this gripper jaw in CAD. You'll export that as an STL, and then you're going to slice it. And slicing is kind of similar to slicing some deli meat. It's going to cut that model into a bunch of really fine, thin layers. And as part of the slicing software, you'll also choose your part orientation in your printer, as well as configure some material characteristics of that part. And finally, that model is going to be then divided into thin layers and generate machine code to tell the printer what to do. So a slicer will take a part geometry like this gripper right here, and it's going to slice it into a bunch of different thin layers. And the end part will look something like this, where it's a bunch of different layers built up to produce that final part. To give you a sort of comparison to CNC machining requires you to do CAM, or computer-aided machining toolpaths. So you have to basically program the toolpaths that your cutting tools are going to take to produce your part. Well, 3D printing is a lot easier. It requires slicing, but the sort of CAM of 3D printing or slicing is all done automatically by 3D printing software. Now, this is the plastic side of 3D printing. So Markforged uses two processes. We've talked about FFF. We also have a process that we developed called continuous filament fabrication, which is how we add high-strength, continuous composite filaments to our parts and make them really strong. So very similar to a more traditional 3D printing process, you're still going to design your part in your favorite CAD package and model your part. You're then going to bring it into Markforged's software called Eiger, where you're actually going to also select reinforcements. You're going to actually choose where you can actually put really high-strength composite fiber into your parts. And that's going to allow you to get really high-strength parts up to about the strength of aluminum. And then finally, you'll send that file off to your printer and allow it to print and produce a part. But to give you an idea of what that process looks like, I'm going to actually look at this actual gripper in practice. So this is also from our friends at DIXON Valve, and it's a 3-jaw coupling, or it's a 3-jaw gripper that grips a pipe coupling. You can kind of see it in action right here as it grips that coupling. So that jaw in CAD looks like this. And for purposes of explanation, because 3D printing software slices apart layer by layer, I'm going to look at specifically this layer in the CAD. So I've done a cutaway here to show you that. Now, I'm going to look at this head on. And so this is the cross-section of that layer, or cross-section of that part in CAD. And this is what Eiger, our Markforged software Eiger, is going to do to slice that part and produce tool paths. So what you can see here is we actually produce a sparse honeycomb infill in those parts. So the white tool paths you see here are our onyx material, which is a chopped carbon fiber nylon blend. So we have a nice sparse infill. And then on the outer shell of this part, we're laying down a continuous strand of composite fiber to add a lot more strength. And when the printer actually produces that, it looks like this right here. And so you can actually see, believe this is Kevlar right here, that's running all the way around the outer shell of that part to add a lot of high strength to this gripper jaw. And what that looks like on the printer, this is on our Mark II, is that right there. So that at that layer, we've added continuous composite Kevlar all the way through that part. So we've talked about how Markforged makes these really high strength parts with both our plastics and composites material. But I want to also show you how easy the process is to design a end-of-arm tool and then have it printing in as little as 15 minutes. So I'm starting with a standard template tool. And this is something that, it might take you a few minutes to a half hour or an hour to design the first time, but every time you need to make a new tool based on this template, you can just start with the template every time and save a lot of time each time you design a new tool. So I've designed this template tool already, and this goes with a Schunk gripper jaw, or for a gripper. And I'm going to then import my part that's going to be manipulated. So in this case, it's this pipe coupling you see here. And I've positioned that pipe coupling in relation to where I want the gripper to actually grip it, but you can see that there's a bit of interference as that coupling is actually located inside the jaw right now. And that's okay, because that's where our Boolean operation comes in. So now that I've correctly located this pipe coupling in relation to where I want it to be gripped by the gripper, I'm simply going to run a Boolean operation and subtract the geometry of that pipe coupling from the gripper jaw. Once that's done, and it's 3 clicks to finish, I'll do a little bit of cleanup operation. So I kind of subtracted away a little bit of the faces and geometry that was left over after that Boolean operation and clean this up. So at this point, we have the geometry and the design for a really nice conformal gripper. The only thing I want to do now is to just make this a little bit more environmentally friendly for humans to handle. There's a few sharp edges right there, so I'm going to add just a few quick fillets. And I'm also going to add actually a couple cutaways for myself to insert some steel machine keys. So one of the things a lot of times these, for instance, a coupling like this might be casted. So you may be worried about the casted surface finish wearing away this gripper. So in order to add some wear resistance and extend the lifetime of this gripper, I've added these square cutouts for a machine key, and I'm going to press them in, or press a machine key into those voids there. And now I've had a really strong wear-resistant surface to my gripper as well. And so at this point, our design's pretty much done. And you can see that this would be, 2 of these grippers would be used to pick up this coupling you see here. So at that point, we're good to go, and we can export that geometry as an STL and bring it into Markforged's software. And from here, we're going to choose a couple quick options to choose our materials, and then we can just hit print and send that off to the printer. And so when it comes down to it, once you've designed and developed a couple template jaws or template tools that you use pretty often or fit the geometries of parts that you're often gripping, it's really easy to quickly do a Boolean operation, subtract away that part from the jaw you're trying to print, clean it up a little bit, and then send it off to the printer. So to wrap this up today, I want to share with you a challenge that a customer of mine, the guys at DIXON Valve, posed to me to help them redesign some tooling for a automated assembly cell that they had designed. So to give a little more explanation of this, I want to show you a short video of this robot arm in action. So the printed end effector jaws are going to pick up a pipe coupling and also a polymer ring. They're going to then drop the ring and then the pipe coupling on this rotary table in one of the set positions here. The robot's then going to pick off one of the couplings that's already finished from this table, and it's going to drop it in the output side of the machine. In the back, you'll see that jaw get pressed, or the coupling be pressed into the polymer ring, and then it goes back and repeats the process. And this is a automation cell that significantly accelerates the assembly step of this pipe coupling. So as you can see, the assembly cell worked, but one of the issues with it, and the one specifically that they were asking me to help with, was that over the course of gripping these pipe couplings, and the jaws are basically going into the pipe coupling and gripping against a sharp threaded surface, as you can kind of see here, the contact surface of those jaws was wearing against those threads. And you can kind of see the wear here, as I'm indicating by the arrow. And what they were finding was that the jaws really had about a 1-month preventative maintenance schedule. So they really had to swap them out basically once a month due to this wear. And so they liked the ability to iterate quickly on new tooling and 3D print the tooling, but they really needed to extend that jaw life in order to be a serious production equipment. So just to give you an idea here, you can see the wear here. That's the wear after about maybe 15,000 cycles on this tool. And that's really what we were trying to design around, was to avoid that wear on that contact surface. So the solution we came up with was to design in press fits for steel dowel pins, such that the steel dowel pins became the contact surface against the coupling. And you can see that right here, where that dowel pin is the surface which the threads now touch off against. And so it allowed the DIXON Valve team to still 3D print the jaws, which allowed them to get really complex designs easily and iterate really quickly and mature their designs quickly. But the steel pins allowed them to resist that wear and seriously extend the jaw life, and this is something that they're using all across their factory now. So this was a great solution, but then the next question came up was, what if that jaw pressure damaged the threads? And it's a fair question. You've basically reduced the contact area by only pressing off against the dowel pins. But the nice thing is that 3D printing offers us really fast iteration cycles. So it was really quick to design a couple different ideas around this problem. So I'm showing you here both an isometric view of that jaw in the corner, in the right corner, as well as sort of a top-down view of 3 of those jaws put together. So this is basically what the coupling would see as that jaw enters the pipe coupling. And the red dots you see here, or in the corner, the red pillars, those are the dowel pins, the steel pins here. So you can see that I have 6 points of contact, 6 line contacts against the jaw. And that was the question we were worried about, was would those 6 contact points damage those threads? So for the purposes of testing this out, in about 15 minutes of CAD, I was able to double the amount of pins in each jaw, and thus drop the contact force in half. And to continue this exercise, I went a little bit further and added 6 pins per jaw. So all this required was a few minutes of CAD, and I was able to send this off to the printer. And so what we can see here is that we started with a baseline design, and after 15 minutes of CAD, reduced the contact force by about 50%. And after another 15 minutes of CAD, cut the contact force in third from the original design. So each of these designs took about 15 to 30 minutes of CAD, and then only required about 2 to 3 hours to print a single jaw. So we were able to iterate quickly, and in the course of a single afternoon, try out a bunch of different designs before we've settled on the final one. And it turned out that in this case, all they needed was the 6-pin original design. But if we had used a much higher force gripper or had been gripping a coupling with much thinner threads, it could have been a completely different story. And this allows us to really quickly iterate through the process to get the tool we need. So to wrap this up, I want to go back to those 4 key ideas that we talked about at the beginning of this webinar. We've shown you how you can cut weeks from your tooling development cycle by 3D printing those tools instead of sending them out for machining. And we've talked about how you can reduce the mass of your tooling by printing a high strength but really light carbon fiber and hollow honeycomb end of arm tool. And that's going to allow you to spend more of your payload on the actual parts you're manipulating, or run your arms faster, or use a less expensive, smaller robot arm. And we showed you how to design a really highly conformal tool simply by taking a template and doing a Boolean subtract on the part you're actually trying to grip. And that's pretty much it to get a really highly conformal tool. And hopefully all of this showed you how it can be a little bit more fun to do some tooling engineering where you're actually getting feedback the same day and being able to put that immediately back into your designs.